Welcome back. This is going to continue kind of our discussion from last time about interest theory, and we're going to talk about sort of some different ways to define the growth of money today. So this is another video from Texas Financial Derivatives covering interest theory topics. And we're going to talk today about how to define other ways to grow our money. And one of the most easy extensions to think about is just compounding more frequently than 1 year. So if we invest our money in our bank up here, for 1 year, we should expect to get some return, right? So we get our money plus a percent times our money, right? But what if we only invested it for half a year? Does it make sense to get to not get any interest at all? Well, no. But the way that we've defined it, with just an annual effective rate, you wouldn't get anything at all because you only compound once a year, right? Once at the end of every year. So we need to define a way for us to be able to earn interest in that intermediary time period, because that's the only thing that makes sense, right? If we invest an initial amount for half of a year, we should get some amount back that's larger than what we initially invested. That would only make sense, right? But the way that we've defined compounding, this isn't a valid value for t. So we need to develop kind of an extension to our formula. The first thing that we're going to say is that you can have the first thing that we're going to talk about is that you can have what's called an annual nominal rate. And this word nominal means in name only, and that's, maybe you've seen it before. It's called APR on a credit card or a car loan or mortgage or any kind of stuff like that. And it's called APR, and the idea is that it's in name only. So it might be a 10% APR, annual. I think it's annual percentage rate, and the basic idea is that maybe it's compounded semi-annually. And so in this case, and I won't write this out because it's pretty lengthy to say, but you would have what's called a 10% annual nominal interest rate compounded semi-annually. And what that means, what they're telling you by that, is that you get 5% interest compounded every 6 months. So the traditional way to notate that would be I raised to with parentheses. Now this isn't an exponent. But we're going to raise it to the 2, and we're going to have parentheses around that showing it's not an exponent. And that's how we denote the annual nominal interest rate compounded semi-annually. That means compounded twice a year. So let's extend that and say the kthly compounded annual nominal rate would be denoted by I upper K. And that's how it's traditionally said, is you would pronounce this I upper K. And that sort of thing's kind of important to know how to say stuff when you see it in math, how to read an equation like it tells a story, right? And so we're gonna say this is I upper K, and that denotes the kthly compounded annual nominal interest rate. So let's generalize that interest formula. So instead of, we're gonna have, so A sub t, the amount at t, is equal to the initial amount times 1 plus the interest rate to the t, right? Where this is the annual effective interest rate. So that's how we defined it before. So let's extend this definition and let's say that the amount at t is the initial amount, not going to change that part, times 1 plus, now we're going to say I upper k over k to the kt power. So this is the compounding frequency, and this is the number of years. So the idea is suppose that you had compounded semi-annually, like what we were talking about up above. So k equals 2. Well, if you keep it in there for 4 years, then you should have k equals 2 times 4 years. You should have 8 compounding periods that occur because you're compounding twice a year for 4 years. So you have 8 compounding periods that occur. So that's why we have this kt up in the superscript up there, or up in the exponent up there. And then this is sometimes called, this quantity here is sometimes denoted J, where this is it's called the kthly, the kthly effective interest rate. I like to sometimes call it J sub k, so subscript k. But that just means that you're compounding, that's what that effective word is, compounding every k periods. So monthly effective interest rate. You're compounding monthly, and so you'd have some quantity that's your annual nominal rate, I superscript k or I upper k, divided by k, and then that quantity is the amount of that annual nominal rate that you're earning for that period k, right? So that's how we're now going to define our compound interest formula, is that we're compounding, that's all we're doing here, is we're just compounding more frequently than each year. So now the natural question to ask is, well, how does the number of times we compound affect how much money we get out of this thing? Is it a good thing or a bad thing to compound more times? And so let's have an example. So let's say that you invest, let's look at 2 different values for k. Let's say that you invest $1,000, and let's say that you invest it for 2 years, and let's say that the annual nominal rate is, so I upper k, the annual nominal rate compounded semi-annually is going to be 10%, and let's say that the annual nominal rate but compounded quarterly is also going to be 10%. And let's see how that affects. So when these are equal, let's see how k, 2 and 4 respectively, affect a of t, the amount at time t. So the amount at time t for, so we're going to do it for k equals 2, and then k equals 4. So for k equals 2, and then here will be for k equals 4. And so this is the amount after 2 years. So t equals 2 down here too. So after 2 years, compounding twice annually, or twice per year, we have 1,000 times, I'm going to plug it in the calculator here, 1 plus 10% divided by 2 to the 2 times 2, and then 1 plus 10% divided by 4 to the 4 times 2. And so when k equals 2, we get $1,215.51 after the 2 years. When k equals 4, we get $1,218.40 after the 2 years. So what's that telling us? It's telling us that everything else held equal, all else equal, including our interest rates, we're getting more money the more we compound. So the natural question is, was there a limit to this growth, or can we just keep going to the bank and saying, I'd like you to compound my interest every day. I'd like you to compound my interest every second, every half second, every millisecond, whatever. Smallest amount of time you can think of. Is there a limit to our growth as k gets big? And so The way that we're going to find out is we're going to take a limit. We're going to take the limit as k gets big, goes to infinity, of the initial amount invested multiplied by 1 plus the annual nominal rate divided by compounded kthly divided by k to the kt. So what's going to come out, and we can pull out this constant. As k tends to infinity. And then we just have the rest of that in the parentheses here. Cool. So, well, we'll think about what's going to happen here. As k gets large, the interest rate is finite. K is going to go to infinity. This is going to go to 0. So everything in the parentheses is going to go to 1 because this fraction here is going to go to 0. And then the exponent, well, that's going to go to infinity. We're raising it to infinity. So it's going to look like this indeterminate form, 1 to the infinity. And we're not going to know what to do with that. And obviously it's not like, it's not the case that this is equal to 1, because then we'd have no growth, and that doesn't make any sense. So what saves us here in this special form of 1 to the infinity is this identity. And the identity is this. The limit as n goes to infinity. You may remember this from Calculus 2 or 3 or whichever one. The limit as n goes to infinity of 1 plus 1 over n to the n equals e. And the more general form of that is the limit as n goes to infinity of 1 plus r over n to the nt equals e to the rt. So that's what's going to happen here is we're going to have this e to the rt fall out of our formula from up above, this limit that we're taking. We're going to have e to the rt fall out of it. And so what we're going to say is we're going to rewrite this limit here. Limit as k tends to infinity. 1 plus I upper k over k to the kt is going to equal the initial amount invested times e to the rt. Now, what is r? Right? T is the number of years, right? That's still the same. That's fine. But what is r? R is the continuously compounded interest rate. And it's different from what's in this formula because this is the kthly compounded interest rate. We need the continuously compounded interest rate in order to have, which is a different number, in order to have our limit be satisfied, in order to have this identity be satisfied. So that's what's going to save us here is this identity from Calc 2 or Calc 3. And so we now have kind of this equality between e to the rt and compound interest. And this is a useful identity sometimes because this relates it back to what you're really doing here is you have this accumulation function and you're relating it back to this other accumulation function. But r and I must be inherently different rates because of what you're doing to each of them. This one is discretely compounded, what you're doing with each of them. And this one is continuously compounded. So this is going to be an inherently different rate than this is because you're changing the frequency of compounding. And so you can relate the two through, you cancel out the exponent and take the logarithm of both sides and you end up with r equals natural log 1 plus I. That's all well and good. And so that's your relationship between the two of them. And so that's like when you have a discretely compounded interest rate and you'd like to know the equivalent rate that's continuously compounded, you can relate them through this formula. And so that's a good identity to know. Now, why we're going through this, why we're even talking about this continuously compounded interest rate, well, it makes sense when we get into modeling options and derivative securities to talk about a continuously compounded rate because it makes the math a lot easier when we derive things like the Greeks, whenever we use it in things like Black-Scholes, and even in terms of just binomial trees and pricing things in discrete time. It's better to assume that the interest rate and actually the dividend rate are continuously compounded. And so we'll denote R will be our continuously, when we get into derivative securities, we'll call it the continuously compounded risk-free rate. And then we'll call delta the continuously compounded dividend rate. So a use case for this would be, suppose that you have a stock which pays an annual dividend that's defined by, say 5% of the value of the stock. So call it stock time. It's the stock value at time t. And so that means that the dividend rate is 5%. But that's annual, right? And so when we get into stuff like the Black-Scholes model, when we get into stuff like binomial trees, we need a continuously compounded rate. And so that's where this identity comes in, this useful identity, because we're going to say that delta, the continuously compounded dividend rate, is equal to the logarithm of 1 plus the annual dividend rate. And so then you get, the log of 1.05 ends up being that the delta is 0.0488. And so it's a little bit smaller rate, but it's being continuously compounded, so it actually is equivalent to this 5% because of that changing compounding frequency. And we're going to use this concept really extensively. You're going to see this concept come up time and again when you're dealing with derivatives markets, and when you're dealing with stock modeling, or really just any of the more formal models. Really like using this continuously compounded rate in order to make the math just that much easier, because taking a derivative of, for example, taking the derivative of 1 plus I to the t power in t. So we're taking the derivative d dt of this, the derivative with respect to t. That's going to look like the log of 1 plus I times 1 plus I to the t. And that's a lot more difficult expression to deal with than d dt of e to the rt, where this would just end up being re to the rt, right? And so this is a lot easier expression to deal with when you're taking a derivative than this one is up here. And so when we get into this particular derivative, will end up being used. It'll be a partial derivative, but it'll be used in determining what the Greek theta is, which is the partial derivative of value with respect to time. And so we much prefer to deal with this notation than to deal with this formulation up here. So we will use this extensively, and that's just a small example. We will use this notation extensively, and so make sure that you kind of understand where it comes from, how it's related to a discretely compounded interest. With all that said, we're going to close out this kind of interest theory topic, and in the next videos, we're going to cover kind of introductory probability and the sort of things that you're going to need to know as far as probability theory goes in order to develop good models for pricing derivative securities, for pricing options. And I hope you've enjoyed this section on interest theory, and look forward to seeing you back for the next videos. And have a great rest of your day, have a great rest of your week, and take care. Bye-bye.